Yeah, this is on. Is it working now? Oh yeah. Okay, let me see this. Yeah. Okay, I'm all set. Yeah.
Okay, so let's start with the next talk. So I'm sure you all know Barbara Terhal has done great work. You know, the thing that I like most is the work she's done on models of interesting models of quantum computation, and she'll tell us about noisy Fermionic.
Okay. Thanks, Umesh. Yeah, I'm glad to be here. And I had the impression that we were expected to talk about deep conceptual topics. And I thought about one project I'm doing right now, which I find interesting and has some conceptual interest, but it's not finished yet. So I'm talking about something that has also technical aspects that I don't know whether you're all ready to parse them or understand them early morning, but we'll see. But it has a little bit of physics in it and some computer science and some math, so I hope that this is the right audience to give such a talk. Okay, so it's about power of noisy fermionic computation, and as Umesh suggested, it is sort of in line with something that I found interesting for a while now, is the boundary between classical computation and quantum computation. So there are models of quantum computation that are restricted, so in such a way that you can simulate it classically, and then you can ask what ingredient do I need to add, what research in order to make it fully quantum, in order to make it really universal for quantum computation. And so you can ask, where does this boundary lie, and that may give us some information about what we would need to do experimentally and implementation-wise in order to achieve quantum computation. So I'm going to dwell a little bit on in the introduction, because I don't want to lose interest when I talk about two subjects that are too technical. So as you all know, most of you know, that one route towards quantum computation that has gotten a lot of attention, is attractive also because we envision using error correction, is to realize quantum computation by having Clifford gates, such the Hadamard, C0, S, and Pauli's, that we believe we could do with great accuracy because we do them in error correction form, using stabilizer codes. But that by itself, the Clifford gates, if you'd have a computation that only uses those gates, by the Knell-Gottesman theorem, we could classically simulate it efficiently. It has no quantum power. And of course, that has advantages, that if you actually have an experiment that would only realize those gates, you could track very well. You could test that device very well by just simulating it classically. And so you need another resource. You need a T gate, a single qubit T gate, to really get your quantum computation going. And one way to do this, so there's several ways of doing this, and one attractive way to doing it is, imagine that you have a certain single qubit ancillas that if you had, if they were perfect and you had Clifford gates, they would allow you to also do a T gate via a trick called gate teleportation. But now those single qubit ancillas, you imagine them to be noisy. So you can imagine that if, so this is an example where you see this boundary. So if you just have Clifford gates, you can classically simulate it. If you have perfect single qubit ancillas, you would get the full power of quantum computation. So you can imagine that if you have noisy ancillas, that you're somewhere at this boundary. So you want to determine for what noise rate can I tolerate, such that that I can still get universal quantum computation. And if the noise rate is above some level on the single qubit ancillas, I may be able to simulate it classically. So this is a subject, yeah?
So Baba, I'm not sure if you're going to use it later in the talk, but I'm not sure all the audience is familiar with S and T.
No, I'm not going to use it. Yeah, okay, so there's a subclass of gates, and there are just a bunch of single qubit gates and 2 qubit gates. Yeah, okay, but I'm not going to use it anymore. So if you don't know it, it's just a... Yeah. Okay, yeah, so this, if you have noisy ancillas, there's a boundary somewhere, and this boundary has been explored. So there's actually, so you can represent states on the Bloch sphere, and then there's a certain Clifford polytope on this Bloch sphere, which is a set of noisy single qubit ancillas, or these points on in this Clifford polytope are noisy single qubit ancillas. And those ancillas, they are actually convex mixtures of states that you could get by Clifford gates. So such a state can be simulated by just flipping a coin. With some probability, you pick this state, which you can get by a Clifford gate, and with some probability, you pick another state. But then there's some ancillas right outside this polytope, where the noise level is 45%, so quite high. They can be distilled. So there's a procedure by which you can use these ancillas together with Clifford gates to realize even more lower noise ancillas, and then you actually can realize the non-Clifford gates and universality. So here, what I want to say here is that the boundary between where classical computation can simulate everything and where quantum computation starts is really sharp at some points. Okay, so this is part of our motivation. So I wanted to look at another route towards quantum computation that has gotten a bit,
Sorry,
yeah?
just
Yeah.
to go back
Yeah.
to so there you were saying, you were really saying, as soon as you step outside the polytope.
Well, it's not on every point, but
Yeah, but
there are points, yeah.
there are points
Yes.
which give you universality, but moreover, even if you step outside and it's extremely noisy, you still get universality.
Yes, so there is a distillation protocol that works right up to at the point where this polytope ends. Yes, yeah. Not everywhere because it's a polytope, but there's one. Yeah, yeah. That's work by Reichert. Yeah. And there are also people who've looked at ancillas, but at noisy T gates. So if I have a noisy T gate, you can say, well, if it's too noisy, I can maybe simulate it by a convex mixture of doing Clifford gates. And there are also some nice results about that, but this is more in line on how we will generalize this. Okay, so there's another model. So the Knell-Gottesman theorem talks about how you can simulate computation using Clifford gates, and there's another model of computation in which you can classically simulate everything, and which is fermionic linear optics or non-interacting fermions, and I'll come to talk about that for a moment. But there is one model to make something universal. So let's maybe I shouldn't have mentioned this. What I want to talk about is something that has attracted, especially in the experimental community, some interest. Is the idea of doing computation using Majorana fermions. Yeah?
Can you remind us what Majorana fermions is?
Yes. Yes, I will. At this point in the talk, I will use words, and in later point, I will use math. And I hope that it will be. I mean, I can give a whole talk trying to clarify this, but I hope that you find it satisfactory. That you can vote up or down and boo and whatever, but depend. Okay, but so now, so why I say fermion. But I mean, there's a way of understanding it mathematically, which is very simple. Okay, so but let's just now do it in words. Okay, so I can talk about a single fermionic mode, which is occupied or not, which is so either 0 state or 1 state. So it's actually just a qubit. Yeah, it's up. Okay. Now, and so I can characterize this mode by something called a creation and an annihilation operator. Yeah, and I can take linear combinations of these operators, and I'll call those operators. And these linear combinations take two different linear combinations, and these two operators are called Majorana fermion operators. Now, this has nothing to do with the physics yet. So there's one way of defining a Majorana fermions, which is just two Hermitian operators that mutually, or well, in this case, two Hermitian operators that mutually anti-commute, that you can get out of one fermionic mode. So every fermion I can represent as two Majorana fermions, period. Except the point is, usually these Majorana fermions, you can't see them as particles because these two operators are just, they're not physical, and they're at one point in space. But so the interest in Majorana fermions is actually you have a fermionic mode which is very non-local, such that these Majorana fermion operators, one is over here and one is over there. And then you can imagine that you change properties of your system such that you move, you sort of adiabatically. Well, maybe I should. So you move this operator around, or this operator characterizes the state, and you change the Hamiltonian, so you change the state, so it corresponds to moving this operator around. Okay, else, boo, ba, I don't know. Okay, so I'll say more things about that. But you can also, you're used to linear optics, so you have creation annihilation operators. You have a P and a Q, right? The momentum and position. So you could, the Mariana fermion operators are the fermionic P and Q.
Oh.
But that's just as an operator. It doesn't, yeah.
Somehow you put the P over here and the Q over there.
Well, okay, so yeah, so every fermionic mode is characterized by creation annihilation operators, but they are not necessarily creation of an electron here. But the thing is with these interesting Mariana fermions is that these creation operator and annihilation operator is very non-local. It's a sum of something here and something there. And that's why it's robust degree of freedom. Okay. So it's one. So if you try to cut it short, you have one fermionic, very special non-local fermionic mode, which you either occupy or not. And the point is that the energy, it costs no energy to occupy or not. So if they say it's a zero mode, so you have a Hamiltonian, and it has a degeneracy. Either you occupy the mode or you don't occupy the mode. It's the same energy. So you have a ground space degeneracy, and so maybe you have this. You have many of those Mariana fermions. So you have a highly degenerate ground space, and now you want to do computation in there. And so you want to change these states, these ground states, such that you do gates on them, and that's what they call braiding with Mariana fermions. Okay, so but actually the way you encode a qubit in this scheme is actually to use 2 fermions, which is 4 Mariana fermions. And there's a reason for that, because if you were to use the single fermionic mode, which is 0, 1, the problem is that the idea is that this mode is protected. That's to say, if I'm in a 0, it's hard to go to the state 1. That's what you want, right? Because that would be a logical error. So, but that also means that it's physically hard to actually do this. So you actually want to not encode the qubit into the 0, 1, you encode it into 0, 0, and 1, 1. So you never have to change. So this is your subspace. So you keep the parity is fixed. Okay, so then there is what you can do with these Mariana fermions if you actually show that they exist, which is still an ongoing program. I think Adi Stern may talk about this later this week. You imagine doing braiding of Mariana fermions. And so I said this fermionic mode is characterized by or captured by 2 Mariana fermions that are long distance. And now if I encode 1 qubit, there's 4 of them. And these operators, these long distance, they actually just characterize this ground space degeneracy, this ground space. And so if I change my Hamiltonian where such that this ground space this ground space changes, what I do is I change the ground space in such a way that I come back, I change it gradually and I come back to the old ground space, but now I've done a logical operator. So there's the idea of topological quantum computation. So you can do that by braiding Mariana fermions. You move these Mariana operators around each other. Okay, but the point is, the point is that this only gives you single qubit Clifford gates. If you do this encoding, and it doesn't seem obvious to do it a different way. So it's very weak as a computational model because it's not even just Clifford gates. It's only single qubit Clifford gates. So then, so this is work by Brav. He said, okay, we do, in order to get universality, we do something that we do as we do for Clifford gates in the other model. We have to use noisy ancillas, or we have to use ancillas, but they'll probably be noisy. And then if we have those ancillas and we have these braiding operations, then we can actually do also C0 and T gates. And then there is a noise level, and he shows that if these ancillas are below this noise level 40%, and assuming that you have perfect braiding operations, then I can get my quantum computation going. So there's distillation of ancillas are possible. I can improve their quality, and I can do, high fidelity C0 and T gates. So this, of course, is then, makes you ask the same question as for Clifford gates. what if these ancillas are noisier? Huh? If I didn't have the ancillas, I only have this braiding of Majorana fermions. Huh? Now, what is that? Now, braiding of Majorana fermions, I'll come to that in a moment, is an example of fermionic linear optics, and that can be classically simulated. So, you can understand if you have very noisy ancillas, you may be able to classically efficiently simulate it. So we wanted to see whether there's a boundary here between classical and quantum computation that maybe is also tight, or how do we even analyze this? Now, one comment I want to make is that, of course, using this fermionic system or description in terms of fermions, your goal is to do computation. So I could say, well, if I have such noisy ancillas that if I do the Bravi scheme, I get a noisy T-gate that I can simulate with the previous methods, then I know it's of no use. So I could use previous results to get some partial results there, but you may be able to use the noisy ancillas for other reasons. So we want to look at a simulation at the physical fermion level, not at the computation. Yeah. Yeah.
Can you say with the ancillas what they look like? So,
yeah, at the end, actually, at the end of my talk, there will be, I'll discuss the ancilla.
because here, the way you described it, it seems like you were doing everything you could already. You have qubits and you have these annihilation operators and you're moving them around. So an ancilla is something that's maybe special.
Yeah, but the braiding, so yeah, I mean at the end of the, yeah, I can show it at the end, but I will do more math soon, so if that helps, I don't know.
Can you just say again what you mean by simulation at the computation level?
So what I mean is that, okay, so the goal of using these ancillas is to not to do some fermionic thing, but to encode qubits and do Clifford or non-Clifford gates.
Yeah.
Yes.
Yeah.
So I can say I have a noisy ancilla, and now I look at what Bravi does with that ancilla, and if I can see that if this ancilla is very noisy, I do a very noisy Clifford gate that I can simulate with the previous methods. Then
I know that's not useful, but of course I could be doing something else with that noisy ancilla. So that's why this simulation, this fermion level is stronger than that, and that's why we're doing that.
The question is, do you want to simulate a particular
Exactly.
general simulation or arbitrary?
Yes, and then we want to do. Okay, thanks for clarifying. Yeah. Of course, sometimes there may be a stronger one that in principle I mean a weak one, by which we can sample from the output distribution of the quantum computation efficiently. Yes. Right. Yes. Okay. So yeah, this is so we already know, as I mentioned before. We know something about this already. If we have something called non-interacting fermions or fermionic linear optics, we can efficiently simulate circuits that use that. I'll come to that more later. And this was done first by Valiant using match gates. So he considered certain quantum computations using match gates and realized that we could simulate whatever they outputted efficiently. So for him, maybe this was a nice suggestion that the whole quantum computation could be simulated efficiently. But then I looked at this and then realized that this was my fermion. So then Phil had a similar observation. So we cast his results basically in terms of fermions to generalize them. Okay, so now the way we cast the simulation in that paper was a certain way, and in this talk I will want to phrase it in a different way, which is using Fermionic Gaussian states. And the claim then is, okay, so we'll have to introduce them because it will make some things a bit more concrete. Okay, so what I want to consider is a circuit fermionic computation, so I have to describe everything in terms of fermionic operators. And the input of this computation is something called a Gaussian fermionic state. And I have n fermions, but n fermions is just the state space of n qubits. So if you don't like fermions, n qubits. But I'm not going to talk about Pauli's, I'm going to talk about a bunch of other operators that I can also represent as Pauli. But it's not neat, sometimes it's more convenient this object is basically a Hamiltonian. So this is like a Gibbs state. And why it's a Hamiltonian? It's Hermitian because this makes it antisymmetric. And these operators Ci, Cj are the Majorana fermionic operators. And for every fermionic mode I have 2. And why use Majorana fermionic operators? Well, sometimes, you know, I mean, one way to say it mathematically is that they call it just operators. They have nice. No. One.
How are these fermionic things? Because you can't apply equation operators.
Here. So, okay, so
Oh,
so here are the creation and elation operators. For every mode, I just take 2 linear combinations, I got P and a Q, and I get Hermitian operators, and they all are mutually independent. So an example of such a bunch of operators are just a subset of 2n anti-commuting polys. So first I can pick 2n mutually anti-commuting polys. That's a way of realizing. Okay, so I have a class of states like this. Now, for any density matrix, not necessarily Gaussian fermionic, I can write something down like the correlation matrix, which is just an expectation value of an operator like Ci, Cj. And this correlation matrix has certain properties that just come from this being a density. And now what's special about the Gaussian fermionic states is that they're fully captured by this correlation. And that comes from Dixeron, which So if I have a density matrix, and let's imagine these are polys, and of course the density matrix is characterized by an expectation value of all possible polys. And these are typically independent. But for a fermionic Gaussian state, I have the following. The expectation value of the product of these two is the Pfaffian of a submatrix of the correlation. So I look at the columns I1 to I to k and rows, and I look at the Pfaffian of the correlation matrix, which I can of course statistically compute, which is Pfaffian. And yeah, well, let's see. There's a sign. No, I don't remember. Well, yeah. There's a terminal to it. For bosons, this would be the Hopfian. It's just a way you just drop this. But you don't have to sign. It's a matching one. Okay, so the point is that so first in quantum information theory, some people work on product states or matrix product states. Why? Because these have an efficient description. Yeah? So they're used widely as ansatses for ground states or in simulations. These are like the states that we can still have play with access to classes. And the Gaussian fermionic states are basically the like product states for fermions. So they're also widely used. So one thing I want to say that there are states. So if you're on state physics, people are used to not necessarily Gaussian fermionic states, and there's reason for this. Is that well, typically fermionic states, you have a certain number of electrons. The number of electrons is reserved. So you cannot have a state where are maybe not entirely physical, but they give, you know, you can look approximated states. And the point is that the physical states may be much harder to work with, analytically or numerically. Okay, so that's, because there's more to be said about that, but I will skip this. So one thing I want to implement, so, you know, we'll probably be this time, I could learn about qubits, right, why you talk about fermions. I don't want to get into it. So in the sense or in the comments, that I think actually, you know, we are sort of maybe less thinking about qubit sort of things in this area. And this may be in our ideal world, in the future world, but in the physical world right now, the fermions and bosons are much more fundamental.
That's not the argument I'm making to computer scientists at all. I would instead say, look, you like to determine it as a permanent, right? Well,
Like
fermions and bosons.
Well, that's another way. Well, okay. Like, okay, I agree. No, fine. No, if you know what, like, if you talk about rumors, you know, I think for many purposes, there's no reason to talk about fermions and bosons. But, you know, if you're interested in computational complexity of physical systems, then the problems pertaining to fermions and bosons, they are the problems that the physicists are interested in. And they are problems that are also, you know, not necessarily identical, or they have different features than the problems that are stated in qubits. No, I mean, in terms of, you can also pursue a maze-like result, but it's, you know, the optimization problems that you know, for example, so Gaussian fermionic states are used in something called Hartree Fock theory, which is widely spread. You know, we have no rigorous analysis of Hartree Fock, and I would invite all the computer scientists to actually work in these areas. But you first have to understand what's here. Hartree Fock theory, Hartree Fock. So mean field theory. So you know, there are interesting, I think, computational aspects, because the real, you know, physicists are interested in having a, you know, a material with atoms, and they're bound, you know, electrons bound there, and you know, atoms are just the background, and I want you to describe this electron gas and its interactions and so on. And that's an interacting fermion system, and that's a hard computational problem. So they use these kind of, for example, these cases of very zero to get a handle on it.
I can say that the connection to the permanent is what got me excited about it. And the fact that the universe actually contains these bosons is a very nice bonus.
But it's also, I think mathematically it's interesting. That is what actually I find interesting. That it gives you structure.
Yeah, but I tell you, you have to implement it sometimes.
Yeah.
So everything you do, you want
Right,
to have implement everything. You want to have anything implemented anytime. You have to go with it.
Yeah. Well, so I mean the fermionic, actually I think the fermions are less prominent in implementation. At least the bosons are more important than well, university, there are no other yeah, the fermions. So that's, oh yeah, sorry, that was the, well, I mean, yes, there are various ways of implementing, there's a paper by Grafin about fermionic computation, which they showed how you would realize universal computation uses fermions. And then there's this thing by Grafin where it used particularly the Majorana fermions and the grading, and then what research we need until us to get also universal computation. Yeah, I think, and also, Well, that's true. I agree. So usually, yeah, that's you know, we work with many body physics, but in terms of qubit realization for future or like it's all thin. So that's how you get your sorry? I don't know much about selective movement. Okay, so maybe I should see if I can actually. Okay. Yeah, actually, so I find it actually very fun. This fundamental thing that you know, energy is particle and the fermion and to symmetrize the wave function. So if you take a product wave function, so it's like by product state, you antisymmetrize it, then you get something that's called single Slater determinant states, and there are an example of Fermionic Gaussian states with a fixed number. So the point is that if you say, well, why do I have to use the equation and later I'll tell you what I mean? It's just that because it's the symmetry that you impose, you are different formulas that you have to use. I guess it's rough to represent it in terms of creation and animation operators of mode. That's why you could say these are the product states for Fermi. But then they also have different properties. Okay, so one more thing about, so what is the fermionic linear operator? So I said, so if I have a unitary transformation, okay, I can write it as e to the I, h, and h is some Hamiltonian. And this Hamiltonian can contain quadratic terms like this, because it's the quartic terms are higher order, although we typically don't have them in physics, but the quartic terms are very important. But if, and now those are the source of the problem, the source of power in computation. But if you only have quadratic terms like that, then you call such a unitary transformation a fermionic linear operator. And these, the why you can simulate them is because if you have a density matrix rho, then and you do this unitary transformation, it's a transformation, it's a real orthogonal transformation on the correlation. So if you have an input fermionic Gaussian state fully characterized by this correlation matrix M, then I can just, if I have unitary transformations happening of this type, I can just do these rotations and keep track of the correlation. So, and I think also one thing, it's not very special, is that, if these CIs are realized by a bunch of anti-linear inequalities, then you say, well, these satisfy Clifford algebra. If I do these unitary transformations, so I get real linear combinations of these C's, so these again satisfy Clifford algebra. Which is, at least a pretty not obviously think like this problem when you do these transformations. And so this is a different model as like the Clifford gauge simulation model. That's why I think it's interesting. Okay, so the bottom line is that if you have a circuit with input Gaussian states, an evolution with fermionic clusters, and maybe some intermediate measurement of some observables, not anything, then you can simulate this expression of correlation. So now, how much time do I have actually? Okay, so now what we want to do is we want to say if my input is not a Gaussian fermionic state. It's some noisy ancilla, and if the noisy ancilla is perfect, it's not a fermionic. So you can maybe believe or intuitively believe that if the input is a convex mixture of fermionic Gaussian states, single ancilla and that's a convex mixture of fermionic Gaussian states, then I can still simulate it. Yeah? Because I basically with probability I pick one of the fermionic Gaussian states in this convex mixture and I run the simulation. It's very similar as we do it. So the claim is that what we like to know, when is a state a convex mixture of fermionic Gaussian states? Okay, so that's basically this was actually all motivation. Maybe it's more interesting than the final. Okay, so if you think about the fermionic Gaussian state as like the fermionic product state. Then you say, well, when is the state of the convex mixture product? Oh, well, that's the separability question. You have answers to. So this is then a fermionic and also separability. So when is the state of convex mixture? Well, okay, you see in the math it comes out similarly, but there's no real relation. I mean, this is just an intuitive. Oh, sorry? No. So it's not, in many ways it's not. But mathematically it has a lot of similarities. So it just, yeah. I mean, you could say, well, okay, we'll just have a convex set, and we need to separate it. We need to have a criterion that determines whether a convex point is in a convex set or not. And what do we do that? Because the convex set is characterized by hyperplanes, and with the witnesses, and the whole all lots of techniques you use for the separability problem you can also use. But there are differences in the sense that, for example, NP with product states, they're characterized by order n parameters, and these pure Gaussian states are characterized by order n squared parameters. This is correlation to n by 2n. Now how, so one thing, for example, you say if convex mixtures of Gaussians would satisfy a weak theorem, and then of course it would be, maybe you check whether weak theorem holds. But this is not true. So if I have a correlation matrix, which is a convex mixture of correlation matrix each for which this weak theorem holds, if I look at now so my rho is a convex mixture of states, each with correlation matrices. This is not the Fatian of the convex mixture. So you need to have some new idea. So you try out many things, nothing works, but then but then it turns out actually we'll have a criterion which is very similar to the separability. So others say, oh, think about this. So one way to decide, so let's talk about separability. So I have a state density matrix on a bipartite space, and we know there's a criterion which says this state is separable or unentangled if and only if there exists a symmetric extension of the state to many parts. That is to say, instead of having a state on a B, I have a state on A and 10 copies of B, such that if I would permute the state on B, the state has to be invariant, symmetric on B. Well, so this is for any, it has to be for any case. But then there are quantitative bounds also. To say if the state is separable for a particular high k, then it's not necessarily separable, it must be close to separable. And the way you can understand that if the state is separable, so the convex mixture of product states, then it's very simple to see that you have a symmetric extension. You just copy down that state for the system B, you just copy it down to many copies. And so this also gives the criterion. So the thing is that whether it's symmetric extension exists, you can formulate a semi-definite problem. So you say, I have a state, rho, and I ask it there to be an extension of it, such that it reduces back to rho, where I only look at A and B, and it has to be permutation invariant, which phi is a permutation on the B system. And does there exist such a thing? And if it exists, well, then you don't actually know. If it doesn't exist, you know that the state cannot be separable. If it does exist, then you actually don't know. The state can be separable, but it also be still within pattern. If I look for an extension to a two part, so it's only one way. So if the program fails, if the semi-definite program fails for some k, it must be. So and then there's a quantitative version that I put here, which is proved by the Fermionic theorem, that if the state has a symmetric extension to a certain party, then it's closed and transformed to be separable. This is very weak. So now we do the same thing. So okay, so let's talk about the this is the technical. I don't know. Sorry. operators, these operators CI, they don't use these views. They cannot. I can define a tensor form if you want, but then if I define that this is this is an end to the state define tensor form, then I have to say how do these operators act on the tensor form, and they act non-locally, which is that in the commute. If they act in one factory, then it's commute. No, it's not at all. Because no bifurcation. Well, it's no entanglement. I mean, I should not call it entanglement. It's just that okay, so I can give you the criterion. But for pure Gaussian states, it's clear that you can. Yeah. Okay. So I showed you this actually earlier. It's the correlation matrix. So the correlation matrix has to obey n times n transpose is less or equal to identity. And we could prove that pure Gaussian state, that it's pure state is the state is let's say I have a pure state and I want to decide whether it's Gaussian or not. And I can just check whether n transpose equals identity. If n transpose equals identity, it must be Gaussian. If it's not Gaussian, it will be less. No, I don't really. I mean, I just say that as an analogy, but mathematically it's not the same. It's very not. But you could say, well, it's a similar program saying I have a descriptive class of states. I take the complex combination of them. I want to separate them, and but I don't see any direct way of mapping this problem of Fermionic Gaussian state onto product state, onto the question of entanglement and separability. I think there's also the number of parameters. Okay, so yeah, sure, yeah, yes, okay, fine, yeah, but okay, so the one result that we have is that we could also formulate the criterion, very similar criteria, so we can say that state is Convex-Gaussian if there exists a Gaussian symmetric state to many properties. And as I said, if I state on the space H, if there's no bifurcation, it's actually very easy to copy that state down k times and have something with permutation symmetry. That's not powerful. So I have something more. It has to be the null space of a certain operator, which is actually the subspace of the symmetric set. So it's a more restricted criteria. So okay, it comes out this way. But now I don't have that much intuition about it. We're still trying to reformulate it in a slightly different way. Okay, but we have a program which looked very nice. So some of the guys went to look at the ancilla. That if you have a quantitative version, so this here's an ancilla. That this is the ancilla that Ravi uses. He asked about it. This is the 8 fermion ancilla. He describes it in terms of the fermion operation. So we mix it with the identity, and then you can ask how much identity can we mix it before it becomes a conversation. So first we try to use the semi-descriptive program to say, oh, then it's no longer Convex-Gaussian. But this turns out to be computation is quite expensive. We didn't get such a result. So we found actually a big computation. So the upshot is that until here, so actually our results are quite weak. Until here, it's distillable. But you say I get uniform computation and I'm perfect grading. P is the probability here of error. Noise, yes, a noise rate. So I have with probability 1 minus P, I have the perfect ancilla. With probability 3, I have the mixed rate. And only for P is 9, we found a decomposition in terms of Convex-Gaussian. So there's a big gap still open. So okay, I think I should just finish up. So okay, so we solved the problem mathematically. We maybe started it. And I find in general, I think I'm interested in looking at computational problems related to Convex-Gaussian state. How hard is this? And maybe there are statements in classic state that I know also in classic market. So
About giving motivation to computer scientists to look at fermionic systems. So maybe another motivation, which is a bit speculative, is maybe this type of systems or circuits built on fermions will be easier for upper bound purposes, because Boolean circuits are notoriously difficult, and maybe things which are more stochastic will have lower bound purposes. It's not to be used for classical computer science, for maybe not classical, but for lower bound purposes.
With the Majorana fermions, I assume that the motivation is that when you have the Majorana fermion, you can do part of your gate set with perfect operations via some kind of braiding or whatever, but because there's still some imperfect operations that are noisy, you're still going to have a threshold theorem and error correction, etc. Is that all correct? Yeah, but that's the idea. So the hope is that you would have a higher threshold for these class of qubits. Yeah. Yeah. Right, okay. Okay, thank you.
Okay, so thank